Okay. Okay. Okay, good morning.
Morning.
Everyone can hear me, right?
Okay.
Okay, let's start.
Morning.
ละครผมอยู่ไหนเนี่ย หน้าจอผมไม่ได้เปิดไว้เหรอ Just a moment ข้างหลังนั่นเนี่ย Okay, we start basic vibration.
Okay.
We are doctor. ตัวนี้ต้องฟังเสียงเพราะว่าไม่รู้ความบอกแล้ว We are doctor, machine doctor. นะแปลหูฟังบอกข้างล่างมาทีหูฟังบอกข้างล่าง Sorry. This is the first time that I designed for. I just decided this training just a couple of days ago. It's the first time. Maybe some it's not perfect, but okay, we will improve better after this. Why we need today a training body consists of why we need vibration, voice vibration, signal and processing. What is ISO 10816? Any better or more accurate? We talk about display signal. Are you sure what you are looking for? Most of people believe on display that show from your vibration tool, like a spectrum. Spectrum is not real signal. Spectrum is processing signal. We will come to this in the end. And the last one is new technique. We have new technique better than today. Okay. Who are we? HYPROWIRA is domain in oil treatment and analysis. ESS is domain in maintenance and inspection tool.
Hello.
I think you have to mute your microphone.
Hah?
Lokalnya banyak.
Iya Pak. Makan sana Pak. Dibilang orang baru nanti perlu lebih mobil pagi ini.
Oh gitu.
Berarti bekerja keras banget. Gak ada istirahatnya dari istirahat.
Okay, thank you so much. Okay, we are domain in maintenance inspection tool, vibration tool, technical controllers here. V-Mer, we do ourselves. We do it ourselves. I will introduce you in the end. We have laser alignment, hammer laser high end, and vibro laser mid end. Our HYPROWIRA selling vibro laser. Okay, it's very low price, very attractive, and we can integrate with vibration tool. Okay, we have Bosco. That's Bosco in Thailand. We are center. Okay, next.
Okay.
Let's focus. We focus on R&D through manufacturing. In the future, we will get new product. UD1D is ultrasonic leak detector up to 500 kilohertz with spectrum. No one can produce this one. We are the first world for this. Can detect direct EMF, or we call partial discharge, direct. Okay. And we also develop the medical tool. We develop RCM software. We will introduce you in future. This ongoing process. This our tool. That's for medical. We help doctor to fighting with coronavirus. Okay. You can see the screen at the right bottom. That's we migrate from vibration tool to medical tool. Digital tool. We have demo and we offer even free trial. It's at HYPROWIRA already. You can contact them. Okay, come to the point. Why maintenance? Definition, the process of making sure that something continue in the same way or at the same level. That's why we maintain. In ISO 1337, we define vibration is a combination of technique and management to ensure that asset performance and meet required function. We have Toyota pickup to carry coconut tons behind it. We have Ferrari to drive 200 kilometers, not 20. That's a required function. What's the mean technique? Condition monitoring is the define is knowing condition is useless if it's will and it will eat your money. You learn vibration. It's no good. We have to learn for something more. Because more you learn, more you fear. Again, I say more you learn, more you fear. More you fear, you lose your money. So condition monitoring, we have to know condition. If you know it, if you eat your money. I found many industrial. They repair the machine, even machine is good health. So we have to manage this. So condition-based maintenance is a list-based maintenance. Vibration is a major role in ICBM. Okay, condition-based maintenance. But don't let it die. That's why we need combination to technique and management. Why we do condition-based maintenance? It's a powerful technique to minimize life cycle costs, maximize output, control risk, health, safety element. We can do it. We have to manage this. I have tuk-tuk for the market, to buy something for the market. Slightly light load, short distance. I need Mercedes to keep my life safe, to drive fast from Jakarta to Semarang. I need Ferrari to drive faster and safer. So we have list-based. I'm not crazy enough to drive tuk-tuk from Jakarta to Semarang. That's list. No manage. We have to manage this. So maintenance, we have to know the machine to manage it, not to repair it. When I work in shell company, we have one strategy we call sweeten asset. You know Sweden, tire, Sweden, water come from your body, so tire, but not let it die. So we have machine to make it your money. Machine it's not for repair, okay, but don't let it die. This is the list-based maintenance. From this photo, anyone can tell me which one is a list maintenance? Anyone is too late or not premature maintenance? You know premature, like a baby. Yeah, babies stay in our mother for 9 months and then born to be baby. Sometimes they're premature. 6 months, 8 months, then problems. Machine the same. We repair it because it needs repair. We don't repair it from time-based. We don't repair it after too late. You see the bearing up there. It's too late. So from this damage, it brings to consequent failure. Not the bearings damage. You have to change another part. Shaft, sleeve, and replace. Bearing like this. Or the second one, you can see the big machine. I put a man to scale up. Became wrecked in pieces. This is a gas compressor in oil field. Come to the left bottom, bearings. This is least maintenance. We repair it when it needs repair. We don't repair it before it's failed. We don't repair it after it's failed. That's why we have to manage risk. How we can manage risk? By vibration, by collision monitoring. This is PF curve. PF curve. If you do early, good time, good position, your cost is $550. When you do predict, I call predict, but it's not predict. No predict on earth for maintenance. People crazy for this. We cannot do predict today. We just do regression analysis or prognosis only. Your cost going up to 2020. And if you let it die, you pay much because the cost became log scale from 550 to 1500. So it's the way. Come back to this curve, the same thing. If you do precision maintenance, only 550. If you do predictive, condition-based, play around with unsafe act, you're safer. And now you pay more and more money for this, okay? Sometimes severe and injured. This is a pyramid. I will not say which one is the best. You will know this by a tool we call RCM. It's the tool for reliability center maintenance. But many industry is misconduct. Slow breakdown, forward. Some machine, let it die, let it break down, no problem. It's no secondary failure. So we have another tool to design maintenance, the way to maintenance. For example, a jet plane, a passenger plane, that's be traveling around every day, no vibration monitoring, no vibration shutdown, right? What we need, that's why we have a tool to define what we need and how. I just compare to doctor. If we're sick, we have sickness, we have to go to doctor. Huh? Okay, sorry, I go fast. Compared to doctor, if you feel sickness. When you see doctor don't put you in the bed and open your body, look for problems. Doctor just examine us by two approaches, physical or chemical. He listens sound, pulse, blood pressure, blood analysis, urea analysis, blah, 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 blah. Okay, now we talk about vibration. We focus on physics. Check. Sound, vibration, heartbeat. This technique in medical we call oscillating. Doctors have to learn how to listen. Heart, lung, airway, intestine in your body to diagnostic what's the problem. We call osculating. Why I say this? Because I make this. Because I make it. I learned about medical. That's why I can develop to medical equipment. Again, machine also like a passion. Okay. So the key challenge is how we manage machine to be like our life, maximize output, good health, minimize resources, save man, money, time, and spare part. We are doctor, machine doctor. We examine, listen, touching, sniffing, tasting. That's why today we talk about vibration. Listen sound, touch to feel vibration, magnitude, and frequency. This is doctor way, okay? But use your sense. It's not standard. Even ourselves, some days good, some days bad. We need to, the same as the doctor. Can you imagine doctor, from young doctor, middle-aged doctor, old-age doctor, who is the best? People think about old-age doctor is the best because skill, but no, they lost their capability to sense. They lost their capability to send the physical diagnostic. But in opposite way, young doctor has no skill. That's why they lack of diagnostic capability. That means middle-aged doctor is the best, suitable, skill, and still have a good sense to diagnostic the physical from our body. But even middle-aged doctor is not the same. Something so crazy. So medical instrument is an excellent tool to level a doctor to be high capacity, no matter who doctor is. But all skilled doctor will have more advantages because their skill will have to cross-check the instrument telling. It is the same. We are a doctor. We have a tool also good for new doctor, tool also good for old doctor or skilled doctor, because he will maximize tool to more advantage than new doctor. The same thing. So vibration is the best operating parameter to judge dynamic conditions such as balance, bearing, stability, dynamic stress, breathing, sound, and acoustic mission also help. Now we can see why we need vibration. That's why we are here. Let's see what happened here. This is power plant in Iran. Break in pieces. This is not peanut machine. This is the best machine. Power machine. Became in pieces. Can you imagine? This is very good machine. The best from Russia. The name is a power machine. Brand name is power machine. The best in Russia. Sleep, bearing housing, break in pieces. Can you imagine? So became secondary failure. A cupping shaft break in pieces to the wall, come to this. The point is, machine talk to us more than half year. Hey, I'm sick. I'm sick. Please help me. I'm sick. Please help me. But no one listen. That's the problem. Okay. Let me stop share first. Okay, carry on. Vibration. What is definition? It's a periodic motion from an elastic body. Hey, louder. Okay, better? Let me explain to the board. Vibration, that means we have two positions. Position A to position B, we have distance. We have distance, we call S. Okay, this standard word. Vibration does mean there is a displacement between 2 points, A and B, B to A and B, B to A. Became A, B, A, B, A, B, A, B. This is a vibration. We know where is A, where is B, where is A, where is B. So this we call displacement. When I move A to B, B to A, B to E, B to A, within how many seconds or how many minutes? Time is a time. So the different distance at different time, it became velocity. Different distance, maybe B is here, maybe B is here, maybe B is here. At different time, its velocity. The way to change distance from A, velocity equal to 0, right? I run faster, come to here, also 0 again. I come here, 0 again. In between, we use max. So the change of velocity over time we come to acceleration. Now you understand a vibration. Vibration definition is a displacement. Look at vibration at a constant time. At constant time. If you talk about shock, it's not vibration. We call shock. Different. Shock is not vibration. Different sign, different subject. Oh, sorry, the same sign, different subject. Today we talk about vibration. We have constant time. Constant. T1, T2, 3T, T4 is constant. Then we can calculation. We have to start with displacement. Became displacement. We have displacement at a constant time. We have velocity. We have the change of speed, the change of vibration in the time. We call acceleration. Okay? Okay, there is definition. The periodic motion of the particle of elastic body or medium of alternate opposite direction from the position of equilibrium when the equilibrium has been disturbed. Again, a periodic motion of the particle when equilibrium has been disturbed. I hold the bell, is not disturbed. Now I change its equilibrium. So we have vibration. But be careful, this one is not simple vibration. Okay, it's not simple vibration. And in your machine has a phenomenon like this, 100 elements. Okay, let's come, no problem. Today we will know this. Okay. Some definition is a mechanical phenomenon whereby oscillating. I oscillate. Okay. From equivalent point the same. But be careful. This. Okay, let's see the video.
Hello and welcome to this presentation, an animated introduction to vibration analysis. My name is Jason Tranter. I'm the founder and managing director of Mobius Institute. Hello and welcome. Hello and welcome to this presentation, an animated introduction to vibration analysis.
Just a moment.
My name is Jay.
Chọn cái nghe ngon ạ. Ôi,อะไรวะเมื่อวานเตรียมไปแล้วเนี่ยแต่เตรียมเครื่องเขาไม่ได้เครื่องนี้ sorry จอยกันนี้ได้ไงเนี่ยมันเปิดไม่ขึ้นเลยดิฮะโอเคมาแล้ว
Hello and welcome to this presentation, an animated introduction to vibration analysis. My name is Jason Tranter. I'm the founder and managing director of Mobius Institute. Now, the idea of this presentation is to take a quick look at all the primary vibration analysis techniques.
Manorom, there is no video.
Yeah, just a moment.
Okay.
Okay, it's coming. This video you can download from YouTube, okay, but very good information. I will help you to explain something, then you can follow by yourself. Let's start.
Hello and welcome to this presentation, an animated introduction to vibration analysis. My name is Jason Tranter. I'm the founder and managing director of Mobius Company or Consult, if we don't do anything about it. And vibration analysis is a potentially safety incidents. We lose production, we have much higher costs associated with the repair. There are a lot of reasons we want to avoid that. So we
He just explained about why we did vibration, the same as I did before, because we are a doctor. So machine comprises of many parts inside. Every part has its own fingerprint, has its own voice, has its own characteristic, okay?
We want to be able to look at those bearings, look at the gears, look at the impellers and so on, and find out what's going on. You know, if we could look at that bearing and tell that it's lubricated properly, installed properly, there's no damage to the raceways, there's no damage to the rolling elements, then we have the confidence that we can go on producing our product and it's all good. But if we see something, then we can act. Same goes with gears, whether they're timing gears or inside a gearbox. Are they aligned? Are they lubricated? Is there damage to the teeth? Anywhere, you know, whatever the case may be. Vibration analysis.
Can you listen clearly? Indra.
Yes, we hear the voice.
Sorry?
Yes, we can see the video also.
Can you listen the voice from explanation?
Yes, we can listen.
Clearly. Crystal clear. Yes.
Lets us look inside the machine. Now, in this case, we've got, you know, the motor driving a pump and a vibration sensor sitting up on top. Now, I'll explain a bit more about that in just a moment. But you may first imagine that, you know, all the vibration is transmitted along and goes up to this point, and maybe from this side as well. And that's one of the things I'll mention a bit more about in a moment. Just where is the vibration coming from, and how's it getting to that sensor? But one of the keys is that vibration analysis, in a sense, enables us to sort of listen. Well, what is happening with the shaft? What's happening with bearings? what's happening with the rotor bars. Now we pick up all those sounds from here, they all combine together into one measurement, but separating them in frequency and some of the other things we'll explain let us do that so we get an idea of the health of each of those components. Over this side, well, that bearing is not in good condition. For the pump, we've got pump cavitation. On the machine head, many machines sound like that, but anyway. Okay, so the way we do this is, as you've just seen, we can put the vibration sensor up there on the bearing, and all the vibration is transmitted, through the machine itself up to that point. The sensor has to be mounted properly. That is very important, so that all those high and low frequencies get up into that sensor. But the fact is, when we mount it up on top, that is sensitive to the vertical motion. Whereas if I move it to the horizontal location, that's now much more sensitive to the horizontal motion. So, for example, if it was rocking back and forth due to looseness, resonance, then the horizontal measurement will tell us about that. And whether it's vertical or horizontal, they tell us, those two positions tell us about radial vibration radiating out. So if there's misalignment, offset, parallel misalignment, or balance, you get a lot of that sort of up and down and side to side motion. But with angular misalignment, for example, and certain types of bearing faults, it's more sensitive in the axial direction. So we put the sensor in line with the shaft, you might say. And also, all the vibration from here isn't necessarily going to transmit through the coupling. So what we really want to do is try to measure at every single bearing to be absolutely sure we're picking up all the vibration, especially these high frequencies that don't travel very far. I'll mention a bit more about that later on. Okay, so our sensor is sensing the motion, in this particular case, what I've described so far, on the bearing itself. Now imagine if this was the shaft inside the machine. And like a lot of my animations that you'll see today, I exaggerate some of the motion. So there.
Again, you see, we have to have displacement first. The first fundamental of vibration, we have to have displacement. For velocity or acceleration, that is the post-processing, the result of displacement.
It's the shaft moving around in that circular motion, perhaps because of unbalance or a bent shaft. And for simplicity's sake, we've put a dial indicator on the shaft. So as the shaft moves back and forward, it pushes the plunger in and out. We see the needle move and we get this pattern. That pattern is a sine wave. It's a pure sine wave. It has a single frequency and a single amplitude. Now this isn't the way we normally measure vibration. In certain machines, and I'll talk more about that a little later, we can use these non-contact eddy current probes, also known as proximity probes. And it is literally measuring the distance between the tip and the shaft. We use those in certain applications. We used to use velocity probes a lot, but now it's more common to use accelerometers. It sits on the bearing housing and senses how it is moving in response to all the things going on inside the machine. Either way, if we only got one force, if you like, one source of vibration, we will see just one frequency and one amplitude. In reality, there are multiple sources of vibration inside the machine. We'll talk about in just a moment, and therefore we have a sophisticated or more complicated time waveform. But if I speed the machine up, you see the shaft is now moving. It has more cycles per second, or more cycles per minute, and therefore our cycles on our little time waveform graph here are close together. Alternatively, let's just push the amplitude up. So if I make more movements, my time waveform is going to reflect that. Now the amplitude is greater. It looks a bit silly there, but anyway, you see the point I'm trying to make. So that's the basic thing. This is one frequency, one signal, one frequency. It's a perfect sine wave. has a certain frequency and it has a certain amplitude. And that's all very important. Now, let's go to a bit of a closer real-world situation. So what I'm going to do here is I've got a green bearing, the grey shaft and grey pulley, and this orange fan sitting here, the orange blades. So what I'm going to do is turn on the vibration that's coming from that grey shaft. Now, just to clarify something, all the vibration is being measured on this bearing with our accelerometer. That's sort of what we're simulating. But what I can do, just for educational purposes, is turn on and off these three dominant sources of vibration. So there is the vibration at the running speed at the once per revolution frequency. If I speed up the machine, then like we saw just before, the waves get a bit closer together. If I have more amplitude, I get a bigger signal. So from this grey shaft, I've got this grey vibration. That's sort of what we saw a moment ago. I'm going to turn that off, and let's have a look at the green bearing now. And on the whole now I've got green vibration, but it's clearly a different frequency. It's a higher frequency. In reality, bearings can generate 4 different frequencies. And those frequencies, those signals, if you like, are not normally simple and sinusoidal. We'll talk more about that soon. For now, let's just focus on the fact that we've got a different frequency because the bearings, as the rolling elements roll around, the interactions that occur are a different frequency from just the running speed. Now, if the bearings were in tip-top condition, very good condition, I actually don't expect to see any green vibration. But as the problem develops, I get more and more green vibration related to the bearings. Let's turn that off for a second. I've got 10 blades on this fan. And if the air flowed through those blades nice and uniformly, I might not get very much vibration. But if there wasn't as much uniformity, if the blades were bent, let's say, or a number of other potential problems, I get more vibration. But this is a different frequency from the two we've seen before. So I've got my green vibration from the bearings, my grey vibration just from the shaft, once per revolution vibration. And because I've got 10 blades, which the way I've set this up, it's a higher frequency than the bearing frequency, we can see more of a problem, less of a problem. Now, from everything that I've described, hey, you're a budding vibration analyst now. If you could see what I'm seeing there, and you see that the little grey waveform is low in amplitude, you'd be saying, oh, good, the machine's nicely balanced. Oops, it's not as balanced as well. Oh, the bearings are in good condition. The bearings are getting worse and worse. So you get the idea. Unfortunately, this is not exactly how it works. Because we don't see those three nicely coloured signals. We see the summation of all three. They add together, they combine to make the housing of that bearing move according to this red line, and that's what the sensor feels, that's what this accelerometer feels. That's therefore the signal that goes up to our data collector. So that's what's happening. That's there. But as you can see, could you look at that red waveform and see whether it's balanced or is a bearing problem? No, it's difficult. So that's why we use spectrum analysis. Spectrum analysis, so there's those three signals again with the red one turned off. There's the three, and I can turn down the bearing and whatever. What I'm going to do is show you that what we've been looking at all along is actually in 3 dimensions. We've got amplitude, time, and frequency along here. If the machine is running faster, the machine generates higher frequencies, so you see them sort of moving off to the right. If the machine is running slower, there are lower frequencies, it's closest to the left. So this is increasing frequency. And we have separated the 3 sources of vibration in proportion to their frequencies. Low frequency, higher frequency, highest frequency. More amplitude, less amplitude. So rather than looking at it in that format, what I'm going to do is come and look at it end on. There you go. That is the vibration spectrum. Imagine there's a grey waveform behind here, a green waveform behind here, and the orange waveform there.
Okay.
Just sort of simplify a bit more. The calculation that does this is called the fast Fourier transform. So sometimes you'll hear Fourier analysis, you'll hear the FFT, the fast Fourier transform. Either way, this is basically what we end up with, and just to keep it simple, I'm just going to line that, oops, get that line back. Anyway, the reason I'm trying to do that and not doing it very well is that what we've shown here is this is the frequency, and I'm simulating this as if right now, that's what I was just trying to do with the knob, make it vibrate at 30 hertz, because I've got 10 blades, so therefore the vibration from the fan would be at 300 hertz. And the better way to say it is, well, this is 1x, 1 times the running speed. I've got 10 blades, so this peak would be 10x. So if someone talks about vibration frequency, you might hear them say, oh, it was the 10x peak. What's the 10x peak? Well, the 10x peak is 10 times the running speed. And a vibration analyst might think, oh, I wonder if there were 10 blades in that fan or 10 vanes in that pump. Yeah, that's the sort of thing. If you look, and I didn't line it up very well, but this green vibration is never exactly 9x or 10x or 3x. It's always 3 point something, 5 point something, 7 point something. It's always worked out that way. But the beauty of all this is that there's the vibration from the shaft, there's the vibration from the bearing, and there's the vibration from the fan. So basically, I might take a measurement one day, and it, let's just say it looks like this. Oops, I turned that too far, didn't I? So it might look like that. No green vibration, a little bit of grey, a little bit of orange. Now, of course, in the vibration world, we would just say that's 1x and 10x. And if I was watching this machine every 30 days, I'm doing tests according to the PF interval. It's understanding the failure modes to say, well, how quickly does the condition degrade? And I've got to make sure that I get at least 2 measurements in the time where it's going from healthy to the time where it is, well, functionally failed, where we are being forced, either because it's catastrophically failed or it's just unable to perform its function. We want to take enough measurements to detect that. It's not so much to do with criticality. Criticality tells us whether we can justify doing it. The PF interval, or the time to failure, it tells us how often we should do tests. But anyway, if I take one measurement and then I come back later and I see 30 days later it's like this, 60 days later it's like this, I can say, okay, the unbalance is growing. And I can decide whether I want to do something about this high level of vibration. Do I think this is going to cause the machine to fail, the structure to fail? Is it creating noise that's creating a quality problem or a noise issue for workers and whatever? But the question I should also be asking myself is this going to do damage to the bearings? Because while we're monitoring the condition of this machine, damage to the
Hello, Kun Manorom. Okay, we start again. Hello, Kun Manorom, there is no sound.
Okay, mana? Aku pengen tahu. Share screen.
Balance and these sorts of faults. So now we've seen the bearings start to fail. The patterns are a little bit different to this, but you get the principle. So we'd like to know something about machines. So we're going to be a real see this has been normalized.
ตอนนี้เสียงไม่ไปเหรอไปเนี่ย Hello, can you hear me? Can you hear
Yes,
me?
I can hear your voice.
Okay. อะไรเข้ามาเนี่ยผมกดนี่ใช่ไหมผมกดตัวนี้ทำไมผมเปิดจอกลับไม่ได้โอเคมาเนี่ยJason, he just said there is always one peak. That is mean one X. I try to emphasize it's not always B. Most of cases, yes, one X the highest, but it's not always B. Sometimes one X is lower than another. Okay, so be careful with this. Don't jump in conclusion that the highest peak is one X.
Now it's in orders instead of hertz or CPM, cycles per minute. But if I do have unbalance, the 1x peak goes.
Hello.
Yeah, hello.
Yeah. What's wrong with the internet? Okay, carry on.
I think your
I just explained about 1x before. 1x is not always. Okay, so don't jump in conclusion when you analyze it. You have to know 1x is not always the highest peak in the spectrum.
Amplifies the vibration of broad now. Misalignment, and this is puzzling, misalignment, because if it's angular, we see it in the axial direction, mostly at the running speed. If we've got parallel or offset misalignment, we may see 1x go up and or 2x, twice running speed, and or 3x, 4x, and 5x. It all depends on the degree of misalignment, the axis where you're measuring, the type of coupling you're using. All those things affect the pattern that you'll actually see. Looseness, imagine bearing sort of just loose, and there's rattling.
no video.
Yeah. อินเทอร์เน็ตเราก็มีปัญหาเราไม่ของเราเองเราก็มีปัญหาบอกยัง
As a result, then we see harmonics. Harmonics occur when the vibration is not smooth. That nice simple sine wave creates one peak.
Again, most of unskilled vibration analysis always stay on X. I just show you a bell. It's not X. There is a bell inside your machine, maybe 50. There is a bell. ตัวนี้ตำรวจเขาไม่ให้ต่อนะบอกเขายังว่าไม่ให้ต่อไม่ There is a bell in the system. Okay. So don't say just X. X. Sorry. Can you hear me?
Yes, now.
Yes, yes.
Can you hear me?
Yes,
Yes,
I can
yes.
hear your voice.
Sorry, I think in my factory now, many people use internet. I just to tell someone stop use internet this time.
Okay.
Okay, in Liu system, it's not just one X. There are many X. So many six now. It's not related to X. Like a balance, like a crack or looseness, is not X. Okay, so be careful. So don't stay on X. X is really easy. 1X, 2X, 3X is really easy to analyze. But many cases, it's not from X. So most of people misleading about X. X is just harmonic.
When there is impacting going on, or the vibration is not a smooth, just sort of distorted vibration, hard to summarize very quickly, we will see, instead of just one peak, we'll see 2, 3, 4, 5, and they may all be a similar amplitude. In fact, they might go up in amplitude or they'll go down. And sometimes see the noise floor, the bottom of the graph.
We cannot see the video, sir.
Lots of different patterns. But one of
It's okay now. Let me start this again.
it amplifies the vibration, and we tend to see the base of the peak sort of broaden out. Misalignment, and this is puzzling, misalignment, because if it's angular, we see it in the axial direction, mostly at the running speed. If we've got parallel or offset misalignment, we may see 1x go up and or 2x, twice running speed, and or 3x, 4x, and 5x. It all depends on the degree of misalignment.
Looking at
Too much experience, and there's rattling result.
This isเครื่องตัวรีบเปล่าเนี่ยตัวรีบดังในเครื่องนี้เครื่องนี้ดูดีโทรมาเขาไม่ได้ยินเสียง
Then we see harmonics. Harmonics occur when the vibration is not smooth. That nice simple sine wave creates one peak. When there is impacting going on, or the vibration is not a smooth, just sort of distorted vibration, hard to summarize very, very quickly, we will see, instead of just one peak, we'll see 2, 3, 4, 5, and they may all be a similar amplitude. In fact, they might go up in amplitude or they'll go down. And sometimes see the noise floor, the bottom of the graph, lift up as well. So lots of different patterns, but one of the keys is not to get locked into trying to remember patterns. Don't be a world chart analyst that looks at a spectrum and then looks up at the world chart and says, that spectrum looks like this sort of fault.
Can you listen this? Don't jump to conclusion. It's not clean and clear like this in the real world. He's trying to say this. Let me repeat again.
A world chart analyst that looks at a spectrum, they might go up in amplitude or they'll go down. And sometimes see the noise floor, the bottom of the graph, lift up as well. So lots of different patterns. But one of the keys is not to get locked into trying to remember patterns. Don't be a wall chart analyst that looks at a spectrum and then looks up at the wall chart and says, that spectrum looks like this sort of fault. What you need to do, in my humble opinion, is become one with the machine. Think about your machines. Think about their failure modes. Think about the technologies that will detect those failure modes. Think about how you should take your vibration readings and where you should take your measurements and so on.
So he tried to emphasize, don't open the chart to see a chart and compare to the signal in front of you and jump to conclusion, that's a problem, that's a problem. It's not. He tried to say you have to know your machine. So that is a simple question. Who will be the best in vibration analysis? Electric people said, hey, I'm the best because electric. Control said, I'm the best. The best is a man who knows machine design. So how to powerful in analyzer? You have to know the machine. It's a multidiscipline in your head. Know the machine, how it's built, how it's designed. Then look at the signal. Then you can interpret.
And if you understand why the vibration changes the way it does, then not only do you make sure that you set up the analyzer to capture that vibration and you take measurements in locations that will capture it, when you see patterns like this or patterns like that or patterns like this for bearings, you won't just think of the wall chart, you'll think, aha, harmonics, what does that tell me? Side bands, what would that tell me? Lots of peaks, high amplitude, low amplitude, all these patterns should tell you what must be happening inside the machine in order to create those patterns. And that, in my opinion, is how you become a good vibration analyst. Understand the machine, understand where the vibration comes from, understand the analyzer and so what you're seeing in the data.
Understand machine, understand vibration. You see, we have to understand the machine.
And then you can figure out what's going on. You not just look at a wall chart and say, it looks a bit like that one. It must be looseness, you know. That's the trouble. A lot of people get reports and, you know, it just says there's looseness. And you know, what does that mean? You know, what do I do? Anyway, another story. So that is basically spectrum analysis. Now, there's a special type of spectrum analysis where we, instead of just looking at the normal sort of range of frequencies, let's just simplify and say, you know, up to 1,000 hertz or something like that. Hertz is cycles per second. Instead, we look beyond that, because it turns out that when we have, for example, a fault on the outer race of the bearing, while the rolling elements are not making contact with that point, there is no vibration. But when the rolling elements come along and make contact with the spall or the crack or whatever is...
He said it's not vibration. He said it's not vibration because it's not vector. It's a scalar. So we have to discriminate between vector and scalar. Okay, this is not vibration. Let me repeat again.
Outer race of the bearing. While the rolling elements are not making contact with that point, there is no vibration. But when the rolling elements come along and make contact with the spall or the crack or whatever is sitting there, we get an impact. And you can see these white waves rushing out. That's called stress waves or shock pulses. If you take any two metallic objects and clack them together, you put a little short stress wave through those two items, and we can detect that. And there's a lot more I could say on this topic, but basically we can detect that because at the very earliest signs of a problem, either inside the bearing or with gears and other sort of metal-to-metal fault conditions like looseness and broken rotor bars, in that earliest stage, we may not see any normal vibration. The amplitude is so low, frequency is so high that we don't see it in our normal measurements. So we need to use a technique that looks for problems like this. So there's a problem on the outer race, a problem on the inner race. Notice it's a higher frequency, but we still see those little white pulses. And if there's damage to the rolling elements themselves. So this technique goes by many different names depending on the vendor. It can be called demodulation, enveloping, shock pulse, peak view, spike energy, HFD, C, swan, and there's probably other names out there, I apologize.
He tried to say there is many techniques to solve this problem. Demodulation, envelope, shock pulse, peak view, spike energy, SFD, C. I tell you, today is no need. Today is no need. Our digital is more powerful than 30, 40 years before. Envelope demodulating, it since I was young engineer. It's not today. That time we used envelope to solve digital problems. That's why we developed envelope. And envelope is not a high technology. It's just halfway rectifying in analog signal. So that's a way to help digital at that time to detect high frequency. Why digital cannot capture high frequency. That's the way to come to the envelope. But today, envelope still help. Today, no need shock pulse, no need peak view, no need spike energy, no need SFD. It's an all day. But people still hack with the past. Today, digital is very powerful. We can do monitoring, we can do calculation, very complex. I don't need today, but okay, it's there today. Spike energy is long time technology. It just check vibrations, resonance, and detect just the number. SFD, high frequency detection. C, also from envelope, from SKF. Shock pulse, it just fourth order analysis over SFD or over spike energy. It's nothing new. Shock pulse cannot detect even when it fell. It can detect its early stage before it's failed. That's why shock pulse meter, they will come with normal vibration. So for example, if you use C3 bearing, C3 bearing, that means it's extra clearance. It gives sound, it gives noise higher than normal bearings, but it's better long-lasting bearing. So if you see C3 bearing in your machine, even brand new, shock pulse will detect problems, even it's good bearing, because it designs special clearance inside to lengthen the service life. That's why that's a weakness of the shock pulse. It can detect early stage, but that stage is not, it hasn't failed yet. So today, just stay on the normal vibration. Today, technology in digital is powerful enough to calculation complex than over this, but I don't say it's no good. Peak will also help. Spike energy, SFD, see, is peanut today, okay? But the main point is everything here is work under envelope. It's come from envelope. Peak view is just undersampling. Peak view is not complex. It's just simple. They just select a bandpass filter and then undersampling by digital. Normally, undersampling is weakness in the digital, but for peak view, he think upside down. He used undersampling to solve really low speed machine with a complex bearings view. So people will help you to analyze bearing. But today, it's good for only low speed. For high speed, I tell you, every machine can do. Today, we talk about 62 or 46-bit digitized. It's not before. 8 bits, 10 bit, 12 bits, 60 bit, no. Okay, even 16 bit also too enough. In your computer, in your car, in ECU, it's only 10 bit processing. In your car, sorry, can you hear me? Can you hear me?
Yes, we can hear your voice.
Hanging again.
Hello, Kun Manorom. Mohon maaf, Bapak-Bapak, mungkin koneksi internetnya lagi ada problem. Halo, Kun Manorom.
You are lost now.
Yeah, we're trying to fix it. I think the internet connection is not stable there.
It's okay now?
Yeah, now we start again.
Okay. Before I just explain, bearing is not a real vibration, it's a sound. So listen, ผมจะรู้ให้คุณได้ยินไหมเนี่ยได้ยินไหมก็เปิดอยู่เนี่ย Hello.
Yes, sir.
Can you hear, right?
Okay, you can.
Yeah,
Hello.
but
You can continue, Manorom.
the voice is not so clear.
Oh, can you hear?
Yes, we can hear.
Yes.
Yes, we can
Okay.
hear. Yeah, we can hear.
Okay, we carry
I can hear you.
on.
If I've forgotten one you're using. But
Before the voice gone, I try to explain a technique to analyze its bearing. We come from demoderation, envelope, shock pulse, peak view, spike energy, SFDC, Berberaba. Is based on the same fundamental envelope. It's based on fundamental envelope. Envelope is not the complicated process, but it was 40 years technology.
Who is the major player on the envelope?
No, before we born.
Oh, okay.
It's a basic engineering. That's why I say it's based on the same fundamental envelope, but they do other things after this. Like a shock pulse. Okay, we leave shock pulse in the last. Peak view, they just downsampling from envelope to help analysis in very low speed. Spike energy is no envelope. It's 100 years technology. I'd say like this. We talk about the hashtag signal that energize a bearing resonance. Today is old technology. SFD, very old technology. C is from SKF, also post-processing after envelope. So we have, when you, and I see many people use SKF, but they follow standard SKF set point. But sometimes he measure machine that different, and you lost it. So if you know about technology, you have to know inside what is set point, what is configuration. But today no need, because digital is more powerful. Before the signal gone, I just asked you about the digital processing in our car. Our car, we have ECU. It's only 10-bit processing. Only 10-bit processing. Still enough for control our car, save our life, save everything. But vibration machine is not. We talk about 16-bit, 34-bit. So today is more powerful than we imagine. So today don't need like this machine, like this technology anymore. But it helps. Like I say, like old doctor. To also help old doctor. To also help new doctor. But you have to understand it's truly. That's why we lost.
Bottom line is they all, in essence, do the same sort of thing. The first thing they do is they filter away all the high amplitude, low frequency vibration, the normal stuff we would expect to see in a spectrum. That is much higher amplitude compared to what we're looking at with these stress waves and so on. So we filter all that away to get rid of it, and then we just focus our attention on the high.
He said we filter it. We filter it. Then focus on the frequency. That's we look at. That's why you have to know how to filter. That is really important. People use vibration tool today, but don't know how to configure inside. That's difficult. I saw many people use SKF MCX 75. Price is about million baht in Thailand. That's about maybe 300,000 million rupees. But inside they said as a tool. Like he has Ferrari for 200 kilometers speed, but he drives 60. I saw many people use like this. It's totally unutilized the machine you have. So we have to understand precisely inside. More very high, very expensive to very complicated. I tell you, very sophisticated instrument, very complicated to use. Don't think it's easy to use because its design is made for very specialized people who knows very deep in vibration analysis. Okay, next. I will go this far because we don't go in the detail because today we just basic, okay?
All sorts of fault condition. Filter all that away to get rid of it.
Filter.
Just focus our attention on the high frequency, low amplitude vibration.
You see high frequency, just filter to detect it, then envelope over it.
And using these techniques, we sort of translate that back to the low frequency part of our spectrum where we can do our normal spectrum analysis and look for all those telltale peaks at the key frequencies for bearing.
But I tell you today no need. Today we can develop program, software to be smart than we ever imagined.
And gears and such. Okay, so that's an important technique which you should certainly be using, in my opinion, if you've got rolling element bearings, if you want an early warning. Now, when we started all of this, I showed
Time waveform is a real signal. Time waveform, or another word, time domain, is the real signal. He called the raw detail of what happened with the machine. It's a real signal. Spectrum is not real signal. Spectrum is just processing. So don't believe spectrum that show you in display. Sometimes you lost. But time waveform is a real one.
You a time waveform. You know, we looked and you know, saw it, and I'll show you that again just if you're not sure. The time waveform is more complicated to look at, but the time waveform can reveal all sorts of fault conditions that you might miss otherwise. So here's a time waveform, and I'll get back to what this means, but it's sort of like having a movie camera that's filming inside your machine and seeing every little thing that goes on as those balls roll around inside your bearing, as the teeth mesh together. It's seeing everything from moment to moment to moment. The spectrum takes sort of like a long record of all that, a whole lot of that film or a whole lot of that recording, and tries to summarize it into a spectrum. And sometimes that summarization process, is that the right word, actually loses information. The time waveform tells us exactly what happened. So we saw it.
He just said when you convert to spectrum, you lose information.
Earlier, you know, as I clicked on the little buttons, you know, these are the individual components of the time waveform. This red one is the raw time waveform. Simplified, but that's the raw time waveform. So in other words, in order to collect this thing called a time waveform, you don't necessarily have to do anything different. You just have to tell your analyzer to store it, because you also want to look at it. Now, the truth is that to do spectrum analysis correctly, you need to look very carefully at the Fmax, which is the highest frequency in the spectrum, and the resolution, sort of like the clarity, the amount of detail in that spectrum. And when you make those settings, that affects the time waveform that needs to be captured to create that spectrum. Well, you need to look at what that time waveform will look like and ensure that what you hope to see in a time waveform will be visible. And that's where a lot of vibration analysts get caught up. They look at the time waveform and they see it just looks boring, it just looks like a whole lot of just blue graph, and they say, that's not telling me anything, I'm not going to bother with this anymore. Please bother. Please just make sure you get the settings right. We spend a lot of time on this in training to make sure you understand why. And what I'm about to show you is sort of a simplified explanation of why people get it wrong and what you need to know. Now, remember I said time waveform analysis is a little bit like using a video camera. And you're probably aware that a video camera records, I think it's 24 frames per second, because when you play those 24 frames a second back, our brains can't tell that it's just 24 pictures that we looked at in that second. It looks like it's all continuous. Well, time waveforms are the same. When we choose the settings for our spectrum, the analyzer decides how frequently it's going to convert that analog voltage from the sensor into a digital.
You see it here, number of sample. 1024 number per second. I want to cry because today some vibration machine still based on this. Please forget it. This really ancient digital. Today we talk about sampling 100 samples per second. No more 1,000 per second. We lost information, but people prefer it because waveform is very clean. So you lie with yourself. Because you lie to yourself. Hey, I want to see clean signal. Be careful. Vibration 2 is different from brand to another brand. The point is There are many Okay, come back. There are so many vibration tools in the market, which is out of date of technology today. Today, we don't talk about this anymore. We talk about 100,000 samples per second. Okay.
Number that the analyzer has to use because it's like a mini computer. And that's what those red dots represent. The red dots represent each time that it converts the analog to digital. It might sound very technical, but it's pretty simple, really. And you can see in this case that all those little red dots follow exactly along the black line, which is, let's call it the analog signal, the actual vibration that we're measuring. So that's all very simple, but what if it was a gearbox, a gear, and it was damaged? Well, we could translate these little red dots onto the surface of the machine we're testing, because if you can imagine, just as the camera takes a whole bunch of shots, it's also like taking little mini pictures at the gear as it's going past. Now, if you watch on the left, you can see the damaged tooth, and on the yellow graph there, you can see that there's only really maybe one or two red dots on that spike of vibration. The bottom line is, I don't want to make it too complicated, the bottom line is we would like to have lots of red dots on those teeth, especially on the broken tooth, so that we know what's going on. And that all depends on the settings that you use. It's important to get the settings right. So, I'll show you one example. Imagine here we have a rolling element that is damaged, and that rolling element, you know, rolls up out of the load zone, and now it's going to go down into the load zone. Well, this is what the time waveform shows us. In the load zone is where the amplitude's highest, out of the load zone is where the amplitude's lowest. So that's the load zone, that's sort of taking all the weight of the machine, and there it is here, and that's not taking the weight, so the impacts are weaker. This time waveform tells me about the nature of the fault condition and tells me about the severity, how many G's of vibration tell me how severe the problem is, and it's something that I can monitor over time. So that's, you know, very useful sort of display. Here we have two gears. If you look closely, they're moving closer together, further apart. Now it's all exaggerated, but if you look at this, it's eccentric. Could be misaligned, could be bent. You know, we see this pattern. But when we look at it as a time waveform, there it is. That's when they're closer together, and in between is when they're further apart. We get this pulsation of vibration. That's when the lower speed gear goes through the mesh, you know, the forces change, and that's the higher speed gear. You can see the little sort of pulsations in here. Now, the spectrum might show us this. These are side bands in the spectrum. We didn't really explain that, but that's just one of the complications of it. Well, I shouldn't say it's a complication, it's actually very helpful, but we see these, all these little peaks, they're called side bands. It means there's modulation. So if we do our spectrum analysis properly with enough resolution, we can see this. But we can see this for a lot of different reasons. When we look at the time waveform, it's telling me exactly what's going on. Here I'm showing looseness. There's the bearing sort of wrapping around. Closely it's sort of wrapping around. Clearance, and maybe there's some unbalanced driving that force, that motion. And here is the spectrum. I mentioned it earlier. We've got a lot of these peaks. That's the running speed, twice running speed, 3 times. These are harmonics. So, sure, I would see that, and in this instance, I'd probably think it was looseness. But when I can look at the time waveform, look at that, bang, bang, bang. Each of those spikes is occurring once for every revolution of the shaft. So it's turning, going bang, bang, bang. Once per revolution, it's looseness. Like with everything in life, the more facts, the more information you have to help you make a decision, the better. Sure, I could just take a spectrum, and in this instance, I'd probably diagnose it correctly. But it is so reassuring to look at the time waveform and say, right, I know what's going on for sure. I know how severe it is. I know how quickly I need to act. And so when I say that some work needs to be done, my confidence level is much higher. I can make better decisions, and we can make decisions that could cost a lot of money if I get them right and save the maintenance work, or if I get it wrong and it fails. So more information you have, better, sure.
I want to explain about this. The reason why rotating looseness come for complex like this. It is of the weakness of spectrum. Okay, because spectrum cannot integrate signal from times to times at constant. That's why it became multiple harmonic. I will come in this later on. Okay.
Correctly. But it is so reassuring to look at the time waveform and say, right, I know what's going on for sure. I know how severe it is. I know how quickly I need to act. And so when I say that some work needs to be done, my confidence level is much higher. I can make better decisions, and we can make decisions that could cost a lot of money if I get them right and save the maintenance work, or if I get it wrong and it fails. So more information you have, the better, sure. And here's the one we saw in the first place. What's actually happening is, as all of these good gear teeth are going through the mesh of the mating gear, we actually get this low amplitude vibration. See in the gaps, you see just low amplitude vibration. But when these two damaged teeth go through the mesh, boom, there they go through the mesh, big spike. There they go through it again. Once per revolution of this gear, we see a spike in the vibration. Now, often you'd be hard-pressed to pick that up in the spectrum alone. It's a once per revolution vibration. There are other things you'll see in the spectrum, but that time waveform tells you perfectly, look exactly what's happening. And there are some cool ways that you can look at time waveforms. We're seeing here that you can mark it off in revolutions to the sharp. You can look at it wrapped around a circle and see that once per revolution it's occurring. All really cool techniques, but it's telling me exactly what's going on. By the way, we should do oil analysis as well, because the pieces of metal are going to the oil analysis with gearboxes. And that, you might wonder, what on earth is that? And you could get all cranky about it. Oh, goodness me, look at all those little spikes. What does it mean? There's not an even gap between them. Time waveform analysis is too hard. And that is a conclusion that a lot of people come to. The fact is, simplifying the story, if I look at a time waveform like that, then 2 seconds later I can move on to the next bit of data, because the time waveform isn't really telling me anything that I wouldn't be able to pick up out of the spectrum. The spectrum translates all of that into useful information. Assuming that we collected the time waveform correctly in the first place, I could look at that, and other than being interested maybe in the...
He said, assuming. He said, assuming. From time waveform to spectrum. Many people know FFT. FFT is a conversion from time waveform Why they use the word FFT? Because they assume fast. So be careful. Don't believe spectrum. But I don't say spectrum is bad. Spectrum helps 80% problems. But don't rely on spectrum only. Another 20%, we need time analysis. Okay, but spectrum is help for newbie, for beginner. Okay. This is fast. That's why Jason said, assume. Oh, let me come to this. My assume based on signal has to be sine wave. Has to be sine wave. That's why they assume again. But we don't call sine wave. We call sinusoidal. Okay, let's assume sine wave, but not sine wave. A time to change from time waveform to spectrum based on first, signal has to be sinusoidal. Second one has to be period. Two things. When I build a ring, spectrum come to this. Juli, good job. Huh? When I ring the bell, I ring the bell 2 times. But the less, this one can convert to spectrum. 2 times here, not come to spectrum. Be careful with this. Now I ring again. Again, huh? All it is, come to spectrum. This one, spectrum confused, and they cannot cover to spectrum. That's be careful. We will come in detail after this.
Severity of it, how many G's of vibration we're seeing. That's all very useful technique in parallel with vibration analysis with gearboxes. And that, you might wonder, what on earth is that? Now, you could get all cranky about it and say, oh, goodness me, look at all those little spikes. What does it mean? There's not an even gap between them. Gosh, I'm confused. Time waveform analysis is too hard. And that is a conclusion that a lot of people come to. The fact is, simplifying the story, if I look at a time waveform like that, then 2 seconds later, I can move on to the next bit of data because the time waveform isn't really telling me anything that I wouldn't be able to pick up out of the spectrum. The spectrum translates all of that into useful information, assuming that we collected.
He said, assume. Yeah.
The time waveform correctly in the first place. I could look at that, and other than being interested maybe in the severity of it, you know, how many G's of vibration we're seeing, that's all I'm really getting out of it. But this vibration is actually from this same gear, but in a healthier state. It just doesn't have the spikes. It's just the bit between the spikes, you know, rescaled and everything. Anyway, that was time waveform analysis. There we do, which also adds information, and that's called phase analysis.
Let me skip phase. Phase for another deep analysis. We talk about reference time. Phase, that means time. It's help for basic requirement balancing only, or to see a machine behavior, how it's shaped, how it's moving. So just skip on phase. Okay, this time we just go to basic.
That come to mind. It could be if to the machine as a whole, how is the vibration or how is the fault condition causing the machine to move? And that tells us a lot about the fault. So if we have a spectrum with a 1x peak and or 2x and or 3x, then there's a bunch of fault conditions that come to mind. It could be unbalance of varying types, misalignment, eccentricity, bend shaft, cock bearing, etc., etc. You can see them there. From the spectrum, it isn't always obvious which of these faults it is. Now, if I was dealing with a fan and I knew that it sometimes builds up on the blades, dust, you know, whatever product, and it was mostly 1x vibration, then I might be right in saying that it's unbalanced. That is the most likely.
Hello?
But do you know the most common reason why balance jobs fail? Because the machine wasn't out of balance in the first place. Someone sees high vibration, oops, that's unbalanced. Even if it's a high 1x piece, it's unbalanced. And so the machine has to be stopped. You know, person gets in there, safety issues, you know, all this sort of work, and then they find out, you know what, it's not out of balance, it's misaligned or something else. So phase helps us understand that. Now, here is what we call single plane unbalance, static unbalance. The fan is very narrow compared to its diameter. All the unbalance is sort of concentrated, if you like, in one plane. And what's happening is, if you imagine a circular motion that we're looking at from the side, the two ends of the rotor, assuming it's supported at both ends, are moving up and down together. They are in phase. Instead, if we look at it on a bit of an angle, if we traced out, if you like, the orbit, or if we traced out the motion that that bearing is going through in the way I'm animating it here, that motion would be circular. It wants to move in a circular motion because of the centrifugal forces of that out of balance weight. So that tells us a lot. From here, if we could take a phase reading, we measure vibration here, and we measure vibration here, and we see whether it's going up together, down together, down together. If we compared the vibration vertically here to horizontal, we would see that they're both going up and down, but there's a quarter of a rotation delay between the two. So if you look at it, it comes out to the side, then up to the top, then out the other side, then down the bottom, then this side, up the top, and so on. There's a phase timing relation. If we could compare the vibration vertically to the vibration horizontally, we would see 90 degrees phase change. 90 degrees because it's 90 degrees between vertical and horizontal, and it's moving in a circular motion. But you might think, well, wouldn't it always do that? No. With other fault conditions, misalignment, for example, just about all of them, it doesn't move in a circular motion. It's very elliptical. It moves in funny ways you wouldn't expect. That's what phase tells you. How's it moving? So we come up with these little diagrams. We say, okay, and the line at the top.
That is a symbol of phase. 0 degree, 0 degree, 0 degree, 90 degree. Now you can imagine how it's moving, how it's shaped. If this one is up, down. That means it's different shape. If you change sensor from here to here and phase change, it's not always here, maybe somewhere. When you learn about in detail in vibration, we will teach about phase. Phase is just something reference. It's not always top. Even you mount sensor on top. But when you move from here to here, it change 90 degrees. That's the way of shape. So when we learn phase, we have two phase. Absolute phase, reference phase, or relative phase. Okay, different. Okay, carry on.
It's sort of like a reference. Rather than writing down the actual phase readings, we just draw it this way. So because the little line's going up in both cases.
Today for the newcomer in vibration, forget about this phase. Okay, otherwise you're confused. But okay, let video carry on.
That means it's in phase. Because one's going, at 12 o'clock and one's at 3 o'clock, that means there's a 90 degrees phase change, and it confirms unbalance. Here we've got, call it dynamic,
you see,
unbalance.
now it's different phase.
The distribution of dirt build up the reference, and here we are at 5 o'clock.
Yeah.
That shows that it's not the.
Again, it doesn't mean it has to be top. It has to be here. But we talk about relative phase. Maybe somewhere here, relative phase.
The pure and simple, in phase motion of static, and for what it's worth, it's not 180, which would be coupled. Phase really helps us to understand not only what's wrong with the machine, but in this instance, how to balance it. If I have an overhung rotor, not only do I get the circular motion that we just saw.
So when you analyze this machine, you have to know how machine built. This we call overhang rotor. That means bearing is in one side. It's hanging rotor. There is another we call between bearing. Motor inside, also between bearing. But now we talk fan here, connect to the motor. Fan is overhang rotor. Okay.
But we also get a rocking motion. Let's have a look. So I'm not just showing the radial centrifugal forces, I'm focusing on just the rocking. And once per revolution, it sort of rocks back and forward, if you like, as that overhung rotor bends due to the, or flexes due to the out of balance on these blades. So it's still circular motion, so our 90-degree rule applies here and here, but we create axial vibration as well. So we measure that and we look at the phase reading. So this is, we put our sensor axially and see what happens. Now this all might be seeming just a little bit complicated. We're diving in the deep end a bit, but hey, look, 12 o'clock, 3
What happened to this end is happened to this bearing. This is the way of overhang. Again, what happened to this end reflect to this bearing. What happened to this end? Defect to this bearing. Okay, that's overhang.
The balance on these blades. So 90 degrees. And if a detector, misalignment. Now I'm simulating it.
Misalignment.
We've got the bolts undone and it's free to move up and down, you know, maybe we're out in space. Because we're going to bolt the machine down, but the forces are still there. So if I put a sensor here and a sensor there, they are 180 degrees out of phase, whether I measure them both vertically or measure them both horizontally. With angular misalignment, not that you can see it, but it's like pushes, pulls, pushes, pulls. We get axial vibration and we see a phase difference between this face and this face. We have to adjust them because we're pointing the sensors in opposite directions, but we will see that 180 degrees phase difference there. Eccentricity might look like unbalanced, but when we put the belt on and so on, we see something funny. A vibration reading taken in line with the belt compared to 90 degrees apart, you know, perpendicular to it, those phase readings are often close to one another. They're sort of in phase. If we higher amplitude, as compared to measured here, we see a 90 degrees phase shift because of amplitude. So with this type of problem, great big compressors, because then you can.
Let me recap first. Even myself, I'm rarely measurement first. Done it. And today, 80% problems is not required first. 80% problem is not required first. And also 20% problems not required first. So don't stay or make you afraid about first. First, just very simple to know motif only. If you talk about rotor, the main important is bearing. If bearing good, 99% machine is good. Okay, unbalanced, misalignment, let's make a problem. It's lead the problem, but it's not a problem. So in reliability, we call in-spin failure. It's not failure. Okay. Unbalanced, misalignment, berpengalaman, lead to failure later on. So we focus on bearing. Good bearing, always good machine. But we solve the problem unbalanced, misalignment, or berpengalaman equation because we want to extend bearing life. Now we come to orbit analysis. Today also don't need. This is for machine that has the bearing stiffness ratio special. It is for mostly for turbo machinery. Okay, it's different. I just give you shortly for overview. And orbit itself doesn't help for motor, compressor, or blower, useless.
Justify the measurement technique. So here is what's happening inside these machines. You've got the journal bearing.
Different sensor.
There's the bearing part with the special metal. And here's the shaft or where it is inside the bearing.
We just want to know how is shaft moving inside.
Sitting underneath this is a wedge of amounts of 90 degrees.
Let's go
What we'd like
quickly.
to be able to tell is just what is the
You
rotor
see
doing?
how it's way.
What is the journal doing within that bearing? In this instance, we have other faults. In addition
To see how
the
lotus
alignment and
moving.
preload and these sorts of faults.
To see how
interested in
rotor
rotor
moving.
dynamics as well, particularly as we go through.
We have
different
K-length
speeds.
inside the bearing, right? That's why we know problems
So
are
in
not.
this instance, exaggerated, but that's the motion at the first critical. Let's say a lot of detail we could go into, but I'd be interested in.
Again, many people misunderstood using normal vibration to measurement vibration to this machine is useless. It's meaningless, I would say like this, okay? Because bearing stiffness ratio has limited, that absolute vibration doesn't make it.
How do I take measurements to tell that's what's going on? Well, imagine if we had our two proximity probes, similar, because that's what the vibration analysis tool.
Conclusion.
The peaks that you see normally
Okay.
relate to the components within the machine. The shaft, the veins in the pump, and circular, that's good. Misalignment. If it gets big, then it could be the oil wheel we just looked at, or oil whip. So there's lots of things we could talk about with all these topics. But what I'd like to do is just summarize what I think are some of the more important points. So spectrum analysis is the most commonly used vibration analysis tool. The peaks that you see normally relate to the components within the machine. The shaft, the veins in the pump, the bearings, and so on. What we do is we take routine measurements according to the PF interval, or the rate of failure, and we look for changes in amplitude. We look for new peaks that are appearing. We look for side bands and harmonics. And generally, we're looking at the pattern to try and tell what's going on and how severe it is and how quickly it's changing, which tells us how quickly we need to take that maintenance action. So we therefore try to assess the condition from the pattern and the severity from the amplitude. But the waveform and phase, time waveform and phase, gives us additional information, as do other condition monitoring technologies. The vibrations and condition monitoring technology, oil analysis, particle analysis, infrared, ultrasound, motor current testing, all routinely checking the condition of the machine. Now, time waveforms show us what happened from moment to moment. It's like taking that movie and analysing every frame in that movie. Okay, as the gears mesh together, is it going well? As the balls roll around, is it going well? It gives us that detail. Not enough people use this tool. There are all kinds of excuses to offend you if you're not doing it. Bottom line is, it's not hard to measure it correctly. And if you do it correctly, it's a lot easier to analyse the data. It shouldn't take you that much longer, but when it helps you, boy, what a bonus, you've got that information. Now, phase, on the other hand, helps us to understand the motion of the machine. That tells us about, it gives us that detail. Not enough.
Time wave for, sorry, I mean, sorry. Spectrum is most common use in vibration analysis too. It helps you 80%. Let me recap about this. I emphasize again, spectrum, somebody called FFT, is an assuming tool. Assume, and the signal has to be sinusoidal or sine wave, and has a period. So when you convert to time waveform spectrum, you lost information. So simple machine in your factory, in your industry, mostly 80% of the problem, spectrum can help you. Okay. Spectrum is for human interface. You are vibration analyzer, expert. You have to expert spectrum. And you have to expert time waveform. The point is, today, if we talk about automatic analysis, we don't talk about spectrum because the little machine calculate 100,000 calculation. So we don't talk about spectrum in the machine. Machine can work faster, harder, faster than human. That's why we have different way in automatic analysis. Today we talk about basic vibration. Human has to know FFT or spectrum. But spectrum can solve you 80% in your problems. Simple. Unbalanced, misalignment, bearing, blah, 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 blah. Gears. This helps you. 80%, you have to go time. And from here, 1% need phase. That's it. That's why he say here, sorry. Don't forget about time waveform, phase analysis, and other condition measuring technique to get complete story. That's why I try to emphasize spectrum is not a magic, okay?
Analysis, where particle analysis, infrared, ultrasound, motor current testing, are all routinely checking the condition of the machine. Now, time waveforms show us what happened from moment to moment. It's like taking that movie and analysing every frame of that movie. Okay, as the gears mesh together, is it going well? As the balls roll around, is it going well? It gives us that detail. Not enough people use this tool. I've heard all kinds of excuses, and I don't mean to offend you if you're not doing it. Bottom line is, it's not hard to measure it correctly. And if you do measure it correctly, it's a lot easier to analyse the data. It shouldn't take you that much longer, but when it helps you, boy, what a bonus that you've got that information.
He said few people utilize time waveform, but in automatic analysis, 100% we base on time waveform, but we spread in 100,000 calculation and make decision, okay? But for the human, we just assume from time waveform to spectrum for human. That's why human no more to win machine today for 80% problems. Human today should use their own brain, powerful, to solve 80% problems. Let automatic machine to help you. Today, we talk about AI, we talk about automation system, we talk about robot. Why? Vibration analysis cannot do it.
From moment to moment, it's like taking that movie and analysing every frame of that movie. Okay, as the gears mesh together, is it going well? As the balls roll around, is it going well? It gives us that detail. Not enough people use this tool. I've heard all kinds of excuses, and I don't mean to offend you if you're not doing it. Bottom line is, it's not hard to measure it correctly. And if you do measure it correctly, it's a lot easier to analyse the data. It shouldn't take you that much longer, but when it helps you, boy, what a bonus that you've got that information. Now, phase, on the other hand, helps us to understand the motion of the machine. That tells us about everything from unbalance to misalignment, looseness, resonance, all sorts of fault conditions that can be picked up thanks to phase. And we may even see, or we often do see, changes in the spectrum, but making sure that we correlate it correctly, what those changes are to what the fault condition is, potentially means the machine failing or not, or getting unnecessary work done, that sort of thing. And my last comment, I made the comment at the very beginning, but I'd just like to repeat it. Some people use vibration analysis almost like a troubleshooting tool. We're taking measurements just like old Joe used to with his screwdriver, and just like an operator might hear that the machine has a problem. We are hearing and detecting problems that shouldn't exist. And we are just often looking for the bearing faults, the thing that we think, oh, well, that's what's going to cause the machine to fail. So let's focus our attention on detecting bearing faults.
Now he just support my word. When you know vibration, just utilize it to list management, not like a tool to tell the machine health, but you cannot decide is appropriate time to repair or protect or not. So most of case, people who use vibration, that lead to more expenditure. But we have to reduce maintenance costs and increase uptime. That's why you have to use vibration tool to manage the list. Let the machine run, but not let it die. So you have many workload to make decision for this. That's for independent signal. High signal, we have to stop. So most of case, when you dismantle the machine, the parts are good. That's why you eat your money. Okay.
All of that is good. All of that justifies the training and the equipment. All of that is important. But you can do so much more. Because if we detect those root causes like unbalanced misalignment, lubrication problems and soft foot and so on, if we detect those early and correct them, then the bearing probably won't fail. And we, depending on your industry, we might improve quality, we may reduce energy consumption. Just a brand new pump or the recently rewound plant is good.
Okay, let me stop this. Okay. So now we know the principle of vibration. Let me recap what Jason explained about this. Basic vibration. Oh, sorry. Let me try again. Basic vibration. It's vibrate. Everything is complex, consists of mass, spin, and damping. It's vibrate, it gives you signal. We have displacement, then we can convert to velocity or acceleration. But it's opposite way. In practicing, we use a accelerometer sensor to measure acceleration, then integrate back to velocity. Different way. The basic start from displacement to acceleration, but real practical, we measure acceleration and integrate to velocity. Why we talk about velocity? Because it's a kinetic energy. We talk about m/2 v², mv². It's kinetic. ISO standards also based on velocity because of this. Because we talk about energy, not vibration. So if you measure vibration and compare to ISO 10816, sorry, we don't focus about vibration. We talk about energy that emits from the machine. Is danger or not? Jason mentioned about phase. Phase is a time reference. You see now he has time reference. You see this here. It's a time. One revelation. This is my reference to say about the motion at the time. Now you know already from Jason, okay? Just change from time domain to frequency domain and assuming. That's why we call FFT, fast Fourier transform. They said fast to mention about you. Hey, don't believe me everything. So we talk about the overall vibration. That means it's from the whole energy, not discrete energy. That's why it helps you to analyze it. So change from the overall vibration to discrete energy. That's why it's spectrum help for human. That is spectrum. You see, it's not complex, only 1x, 2x. It's so many x, and so non-x. Some machine, they just said, hey, we have overall number. We have synchronous number. We have non-synchronous number. That is telling you, hey, that machine in front of you, I can convert from time to spectrum how many %? But people never notify this. This is the first. We talk about acceleration, velocity, displacement is the same. Again, vibration starts from displacement. From displacement over time, we have velocity. From velocity over time is acceleration. It's the same. Just measure what time at 90 degrees different only. It's the same thing. Okay. When you talk about the scale factor, our electrical is 220 volts, right? That is RMS. Our electricity is a pure sine wave measured in RMS. That's why it tells 220. If you change from RMS to P, you have to multiply by square root 2. That means we came to 317 volts, not 220. We talk about P to P, that means it's 642 volts, P to P. So when you talk about the signal, you have to mention RMS or peak to peak. I recommend you to stay with RMS. But some countries, they use 0 to peak. We don't use peak to peak. We use peak to peak only displacement measurement. Because we have to know the motion from A to B, B back to A to B, B to B. Is real displacement. That's why we need displacement. Again, we measure in absolute vibration, we stay on RMS or peak only. But when you measure, you have to stay only one, otherwise you confuse. The difference is each country use different. Oh, and you cannot convert back and forth. We convert because it's assumed it's a sine wave. No sine wave, you cannot assume like this. Yeah. So based on RMS, it's 0.707 of peak. This is based on sine wave. But real signal is not sine wave. So be careful to convert it. Again, displacement, distance, speed, velocity, acceleration, speed over time. Okay. We talk about line acceleration. I'm on to climb. People still stay with 400 lines, 800 lines. It's about time. Today we talk about the bullshit vibration signal should be at least 1,600 line. Bullshit vibration too. But people still use 400, 600, 800. I don't understand why. I asked myself why they still use this. Oh, I got the answer. They are afraid signal. You see, if we talk about the different line from left and right, from left side, you see clean signal, only one peak, 3570 and 7200. When you go to high resolution, at 7050, you have another, something like this. Okay, so it's more line, it can segregate between two signals. From the right is a low line, low resolution, two signals is crossed together. Many cases, people cannot discriminate between misalignment and line frequency for two-pole machine because it's almost superimposed. That's line today. We talk about minimum is 1,600 line. Bullshit signal, bullshit vibration today has to be at least 1,600. So if you have machine 400, ask yourself why you set this value. Maybe machine has limited itself or by your own fault. I saw many people still use this. Even machine is very good. Because you want to lie something in front of you. Oh, I cannot see really complex signal. So good machine, good instrument give you more detail that make you scared really complex. Accelerator, that's the nature, the normal today. We use accelerator to measure vibration and convert to velocity. Why? You can use velocity sensor as well, but you're losing information because it limits frequency. Displacement is different. Okay, we talk about real displacement, so different sensor. If you talk about velocity, you have a blue line, a blue spectrum. We talk about the acceleration, we have red spectrum. This is a real one. If you have velocity, you have limit low frequency, limit high frequency, but it's flat. It's good, it's ideal, but you lost information, low frequency, high frequency. If you use acceleration sensor, you have poor information in low frequency. We have good information over good to high frequency. So we integrate it to velocity. That's the way today to being used. Resonance, we come this later on, okay? People also mislead about resonance. We come it later. Okay, now we stop this. Displacement, velocity, acceleration is the same, depend on time. Just only time different, from 0 to 90, 70 to 180. Just different time or different phase. At the bottom, I just emphasize, be careful FFT. Spectrum has weakness to convert random signal. I just show you, I ring the bell. Bang, king, 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 king. It's a random. That's the way it's coming. The fundamental, we have to have displacement. From displacement, we can differentiate to velocity. From velocity, we can differentiate to acceleration. And from acceleration, we can integrate velocity, integrate back to displacement. This is integrate from time to time. From time to time. We integrate time to time from v over dt, so it became velocity. We integrate, double integrate, velocity became acceleration. That is the way. Forget about the theory we are using, but you have to understand the fundamental. Again, displacement, velocity, acceleration are the same. Just different time. Now let's just compare to this. Just different time. Just different time. Okay. At the bottom, if we integrate, it became this. Again. Then we have flat frequency response from low frequency to high frequency. That's the way we use velocity to analysis, to verify, to make a judgment, machine good or bad. Don't use acceleration. Acceleration is give you over in high frequency. And people scare, oh my God, it's high like this, but it's not. When you want to judgment, stay on velocity. On standard, everything we stay on velocity. That's way of measurement. At the left side, you see no young people. No way. Only skilled people. We have to gain experience, machine, signal, everything, then they can measure and measurement. Below is myself. That's myself. I measure in the paper industry, okay? But I use automatic. And then I never used before because my people who know nothing about vibration became wizard because it's automatic. This is our machine. Okay, let's skip it. We talk later. We have to understand the signal. Vibration has free vibration, forced vibration, undamped, linear, nonlinear, deterministic, random. Can you open? I want. Dunadi, Hendra. I want to share this. Can you see this?
Which one? Apa judulnya? What is the title?
What is the idea? Don't need to do that. And different Zoom.
Oh, I can. I
You
cannot.
just open the multiple, right?
Yes, now it's multiple.
Okay, let's see. I try.
Bukan, maksudnya multiple. Itu kan saya ada multiple participant. Saya klik.
Just a moment. Oh, ไม่ทันใจเลยเว้ยเปิดไม่ได้นี่ก็ได้ Just a moment. Tôi repeat ไงดี โอเค โ Talk about, start with free vibration. Okay, we go to before free. We go to another vibration.
Sorry to interrupt, Kun Manorom.
Yes.
We have 30 minutes more left.
And
Yes,
then after that, what?
and then we will start at 1 o'clock p.m.
Just open, keep like this, go for lunch and coming. You just stop a video. Better.
Yeah.
Okay, you explain to the audience. Hello? Hello?
Yes, you can continue.
Okay. We talk about force vibration first. Again, sorry. You have to classify a signal. Vibration has the two kinds of vibration, free vibration and force vibration, and then undamped, damped, linear, nonlinear, deterministic, random. Spectrum cannot convert random, cannot convert nonlinear. The less deterministic, periodic spectrum can convert. Okay. We talk about force and free vibration. I ring the bell. The moment I hit the bell, I force. The rest is free. Again, I force. It's free. That's why here, I force, then free. I force and free. I force and free. I force, free. Force, free, force, free. That is the way of free vibration. Okay, now we go to the real one. No surprise. I will change video to the real rotor. Just a moment.
Hello. 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 Hello.ให้เขาดูใน Galaxy Tab
จอนี้ไปเนี่ย
ไม่ใช่อันนี้ซูมของอีกอันนึงไงบอกให้เขาไปดูที่อ๋อ
Can you hear this display now เสียงไม่มีตอนนี้นั่นเลย
Hello.
Hello, yes, yes.
Still there?
Yes. We hear your voice. Yeah.
Yes, we can hear and we can see.
Give switch to the Galaxy Tab S5. Anh nói mày đi.
Just comment Juli Okay. Sorry, my mistake. We kicked the power cable. Hello. Okay. Can you hear? แต่ผมกลับไม่ได้เสียงตรงนี้ Hello. ตอนนี้เสียงนี้ไม่มีนะพูดถึง Hello. Okay. Now we talk about vibration. You have see the spring now? Now we vibrate. You see it's vibrate. It's vibrate. You see the mode shape. It's both shape. And then it's faster. It change to seesaw. A spring vibrate because this one force is force vibration. It's force here, but its shape, it became its own mode. From first mode to second mode. Now I try to demonstrate to you a free vibration. A mass is here. You can see a mass here inside. It's checking inside the mass. Now I put at the lowest vibration. It's no vibrate. It's steady. It's no vibrate. Now I move. Now you check right here. I move. It check right here. This is free vibration. I change frequency. It's no vibrate. I change frequency. It's vibrate. It's go out. I change it bit. You see it? I change it bit. It stop. This we call free vibration. Okay, thank you. Go back. Okay, sorry. Now I connect this one to shock absorber. This acting as an absorber. Now 3 lines is vibration. Now I put here, I damn it. Mode is changed. You see it? Mode is changed. It's damping. We go back, we go in detail after this. This we call damping. Spring, mass, and damping. I remove damp. It's very bad. I can use mass stiffness to tune. It's also mass change, mass stiffness change. That is the way of free vibration from force vibration. This force vibration is free vibration. So the behavior of the vibration depends on mass, spin, stiffness, and damping. Okay, thank you. We go back. I think maybe seeing. Oh, okay. We have about 10 minutes left before we go for lunch. We finish this. Now we just know free vibration and force vibration from the real one. But I just make it simple as a spring and mass. It's happened into your machine, to your equipment. Okay, now we see another force. This machine is give from exciting. Exciting, that means force vibration. And it gives the result at the same. It gives you displacement. Okay. Then when we measure acceleration and integrate to velocity. Or indicate again to displacement. That is the way. Ah, sorry, I didn't share. Let me come again. Sorry. Let me make it again. Make it away. Yeah, make it. อันนี้เปิดไม่ได้ต้องเปิดที่นี่อะไรเนี่ยจำไม่ได้อยู่ไหนฮะเปิดแล้วไม่ขึ้นไงไม่รู้อันไหนปิดเนี่ย
ต้องแชร์จากนั้นเลยต้องแชร์ทางแชร์จากที่ภาพเปิดแชร์
นี่แต่อันไหนนะพี่เดียวผมใช้แบบนี้
แชร์จากสกรีนเปิดได้ต้อง แชร์เปิดแชร์ใหม่จากสกรีนเปิดวิดีโอ
เปิดยังไงเปิดไม่ได้
เปิดตามลิงก์นะเปิดลิงก์ของผมมาของไหนไม่ได้เปิดเปิดกล้องเลย
Okay, now you can see the machine is running exercise, okay, and then give you the result. It's displacement. The real one, we use measurement, acceleration, and indicate to velocity, indicate to displacement. The real one, real world happening, it starts with displacement first, exciting, and then give the result. That is force vibration. Another force vibration. Just a moment, difference. Maybe crazy now. You share. What's the hell? Oh, look at it. Bekerja. Hendra. Hello.
Yes,
Can you hear
hello.
me?
Yeah.
Okay, I think we stop here and start 1 o'clock. Let me set up video during lunchtime. Come
Yeah.
back 1 o'clock.
We will. I think we will continue after lunchtime. Is it right?
Okay. Yes.
At 1 o'clock p.m.
1 o'clock. Yes.
Ya, buat bapak-bapak semua, mohon izin kami ingin sedikit mendokumentasikan, kalau bisa di share page-nya, videonya di ini, biar untuk kenang-kenangan kita juga.
If no problem, just leave Zoom. Continue. It's up to you.
Yeah, I think it's better after lunch, Kun Manorom.
Okay.
We will
So
take some picture to our documentation.
Okay. So you have to save your video. It takes time hour as well from your record. Okay, you can stop. Yeah. Thank you. See you at 1 o'clock.
Ya, see you 1 o'clock. Oke, saya take picture dulu sebentar.
Belum semua, Pak.
Ya, sebentar. Nanti saya pindah dulu lagi. Bentar, Bapak-Bapak. Mohon waktunya sebentar. Saya stop dulu.
Okay, go to lunch, Ben.
Pak, minta tolong videonya ditampilin, Pak. Mau di screenshot bentar.
Udah ada.
Ya. Share lagi.
Tori, please do not share the document. We won't take some picture.
Not share, right?
Yeah, not share. Oke, yang terhormat Bapak Ibu sekalian, terima kasih atas partisipasinya di webinar session pertama. Nanti kita akan mulai lagi di session kedua jam 1. Also, thank you for Kun Manorom for your sharing with us. We will continue at 1 p.m. Thank you, everyone. See you after lunch.